this computer. Good. So we're recording now. More students are coming, and I'm going to start sharing my screen here with you. Let's take a look at the syllabus, where we are at this point. We go. Okay, we start laws of motion Monday a week ago. We cover a little bit of laws of motion again. And what we did last time, we finished first law of motion. And now we are going to start with the second law of motion. The exam is by then, 2 weeks from now, right? 2 weeks and a half. On the 30th of October. Right now I am chapter 1, let's see. Yeah, right now we have lab 1, 2, and 3. Right now we're scheduled to have this material for the second exam. It may change, okay, depending on how much material we cover up to them. Let's concentrate on the laws of motion for now. And this is okay, and lab 2. Okay, and that's Monday. Last time we finished the first law of motion. Okay, first law of motion involves objects that are either at rest or moving with constant velocity. Okay, and what does it mean? It means that their acceleration is equal to 0. That's what the first law is all about. Objects that have an acceleration equal to 0 are subjected to a net force that's equal to 0. Okay, so objects that have A equal to 0 always have a net force equal to 0. Okay. And now you are going to see that first law of motion is not exactly a law. Okay, now you will appreciate that what we call in many books, right? What we in many books call the first law of motion, is not exactly a law, but a corollary, a consequence of another law. Another law. And this other law is the second law of motion. Okay, and how is it stated? I'm going just copy the first law of motion that I had here at the top. Let's see here. Yeah, I'll get this one here. I'm gonna need it, but I'm gonna modify a little bit. Okay. Second law of motion states the following. The second law of motion states the following. An object of mass m is subjected to a set of forces, comma, the net force applied to this object, and I'm going to be more generic. Instead of an object, I'm going to say either an object or a system, okay? This object slash system can be written as, okay? That's the first law of motion, right? The second law of motion is slightly different. Is mass of the object times the acceleration. Okay? The acceleration of the object. Now you can understand what I meant. Why I said that, let's put here, second law of motion. Why I said that the first law of motion is a special case of the second law of motion. This first law of motion is a corollary, right? To the second law of motion. Okay? Note C. From the above law, that you have to memorize, okay? From the above law, that if an object is either at rest or moving with constant velocity, its acceleration will be equal to 0. And the second law of motion reduces to the first law of motion. For this reason, we say that the first law of motion is just a consequence, or is a corollary. That a corollary is all about the consequence of something else. Corollary of the second law, okay? Do you get the idea of a corollary? What the corollary means? It's just a consequence of something far more basic. Okay, this, don't forget, memorize that. And we solve those problems in the same way that we solved the problems of the examples, right? The same way that we solved the examples that I showed to you last time for the first law, okay? And let's take a look at the book. Here you go, here's the book. Concept of force and mass. I'm going to put this thing side by side. Yeah, right here. So you can situate yourself in the book where we are. Okay, so what we cover so far, the concepts of force and mass, okay? Force is a push or a pull. Force is a pull or push. And mass, oh, here you go. And mass, let's see here. Yeah, let's put a mass is a measure of the amount of matter an object has. Okay, that's what the mass is all about. And then going back to the, here you go, 4.2. 4.2, we cover 4.2, right? Newton's first law of motion. We covered that. Let's take a look. 4.3, we are covering Newton's second law of motion. 4.4, the vector nature of Newton's, not just Newton's, the book says Newton's second law, but it's not just the second law, but Newton's first and second laws of motion. Okay. Then we have a third law of motion, Newton's third law of motion, which I like to tell my students the most difficult one of the three laws. Then we are going to cover the types of forces. Types of forces. I already start covering some of the forces that we have, right? Overview. So I covered that already, part overview. I'm gonna boldface what I have already covered. Here you go. Then we have one more, several other, right? 4.7. Gravitational force. Didn't cover that yet, so I'm going to take it out. Gravitational force. Oh, the normal force, I covered the normal force, right? Let's see, I covered that partially. I said that the gravitational force is mg, right? But there's a little bit more to talk about that. There's something else. The normal force, I covered that. The static and kinetic frictional forces. I also mentioned that. The tension, man, look at how many things we have already covered, right? The tension. Equilibrium applications of Newton's laws of motion. We did that too because we came up with several different examples in which the object was under equilibrium. Under equilibrium means the net force is equal to zero. Okay? No equilibrium applications of Newton's law. Newton's law of motion. Okay, that we didn't cover yet because that involved the second law of motion. Okay, so let's highlight what we have already covered. Those. That would be here the examples. Examples that we did in the class for first law. Look how much stuff we already covered, right? More students coming in. So here you go. That's what we have for Newton's second law of motion. Can you remember that? Let's go try to do some examples now. For one, for 2, for 3. Here you go. Newton's second law of motion. Okay. Net force is just I'm gonna here write this equation here of net force. Okay, so I'm gonna put here F sub I, right? We had something similar for Newton's first law of motion. Suppose that we have any forces applied to the object. So you have the summation that goes from throughout the whole, a summation through every force that is being applied to the object. Okay. And let's take a look according to this equation. According to this equation, we can now find out what is the unit of force. Okay, so here we go. Let's get this equation again. Copy and paste it right in here. And I'm going to put that symbol of unit. Okay, the unit of the net force, or the unit of any force, is equal to the unit of m times a, which can also be stated as the unit of m times the unit of a. The unit, we're doing dimensional analysis here, right? The unit of mass is the kilogram. The unit of acceleration is the meter per second squared, right? I mentioned to you before that this unit shows up with so much frequency that we end up giving it another name. Okay, we call it the Newton, N for Newton. That's the unit of our force, kilogram meter per second square, which is also known as the Newton. Okay. Now, one more important thing here. Here you go. I want to write that down here. Don't forget that this equation is in this vectorial equation is in reality 3 scalar equations. If the motion is being undertaken in the 3-dimensional space, right? This, what you see right in here, can be written down in terms of 3 equations. A force, a net force along the x-axis equal to the mass times acceleration along the x-axis, along the y-axis, and along the z-axis. Okay? And now we can come up with a very simple problem. Okay, here we go. Example 1. An object is under free fall. Under free fall is subject only to its weight. Find its acceleration. So we gotta to solve this problem, we have to get do a free body diagram. we come up with a free body diagram, and we must identify all the forces that are acting in this object, okay? The mass of this object is m. Put it right in here. Okay, and I'm not gonna put m, I'm gonna put weight only. And we worry about because we have just a single, the problem told you that we have a single force only, right? Is under free fall is subjected only to its weight. Here you go. The example, right? The problem is stating that there is only one force being applied to the object. Because there is only one force being applied to the object, what does it mean? It means that this object is subjected also to an acceleration. Here you go. And by the way, we are better off writing those equations in vectorial format, okay? Here you go. I'm gonna write that down here. Okay, I got it. And now, vectorial format, increase the size. Now, the m we're gonna leave like that because m is a scalar, right? And the acceleration is a vector as well. Note that the acceleration, note from the equation for Newton's second law, that the acceleration must have the same direction as the net force, right? Going back here. Going back to our second law of motion. The acceleration must have the same direction as the net force. Because in this example, we have only one force, the weight. It means that the acceleration must have the same direction as the weight. Okay? So going back here. Yep. This one. So that's how we usually solve this problem. So we start, for instance, with the mass of an object, right? Where's the step? First step, we draw an object. There's a mass in there. It's not being supported by anything. It's just in free fall. Okay. In the next step, we draw all the forces that are being applied to the object. This is the simplest type of problem that I'm going to see out there for Newton's second law. Simplest one. Because it has just one force. Once you identify the net force, the acceleration must have the same direction as the net force. Okay. And so here you go. Let's not this one here. So now we apply Newton's second law of motion. The net force in this specific case is going to be the weight. There is only one force being applied. And we saw before that the weight is going to be the mass times the acceleration of gravity. And by the way, this acceleration of gravity is a vector. Is a downward vector. Okay? And now we get back to what we already know. An object in free fall has an acceleration of equal to g, right? Here you go. Mg vector is equal to ma. M cancels out M, and the acceleration that we want to find is equal to this quantity here. It's equal to G. Okay? That's the simplest type of example that we're gonna ever see for Newton's first law of motion, second law of motion. And then we have this second example right here. Object of mass 1 kilogram is resting over a horizontal frictionless surface. A force of 1 Newton is applied to this mass along the horizontal direction. Don't forget frictionless surface. That's another level. This example here is another level of difficulty, a little bit higher than the previous one. We gotta go back first, draw the object. 1, draw the object. 2, draw the surface. Okay. Let's see here if I have it here. I have to draw something else here. That would be example 1. Example 1 in the notes. And now we're going to do example 2. And I'm going to use those drawings here to make it easier for me. Okay, first draw the object, mass M, 1 kilogram. Next, you draw the surface that the object is resting. There you go. The surface the object is resting. Next, you identify the forces that are being applied to this object. One force that is always there is the weight. Okay? And then there is this other force that's being applied to the object that's going to be the normal force. Okay, and here we go. The normal. This normal is preventing the object from keep on moving downwards. Okay, and here I'm going to write it down, the fourth normal. Do we have another force? And I'm going to do the following. I'm going to put the like color is like letter, right? Here you go. I'm going to put this one as green. Like color is like letter, is like vector. Playing the movie, right? Let's see, let's look at the problem again. That's how you solve those problems. We have to keep on consulting the enunciate of the problem over and over again to make sure we didn't miss anything, right? So here you go. An object of mass 1 kilogram is resting over a horizontal frictionless surface. A force of 1 Newton is applied to this mass along the horizontal surface, along the horizontal direction. So we must have another force, a third force here. Then I'm going to give it another. Here you go. And different color. Okay. And I'm going to take advantage of those letters. Force. And I'm going to put it with the blue color. someone is applying this force to this object, the frictionless surface. So there is no force of friction right here. Okay? And let's not forget the X and Y axis. Unfortunately, I don't have the X and Y axis here. Oh yeah, I have it. This one. X, of course the Y, and the X axis. Okay, here you go. The axis was supposed to be drawn much earlier, but that's okay. Let me see, I don't need that here because the next one already been drawn, right? Yep, I got it. Let's play the movie. Oh, that's gotta correct that, right? Example 2. Here you go. Mass, surface, weight is always there. Normal is there only when there is a contact between the mass and the surface. And then we have this additional force of 1 Newton. That's the problem, the statement of the problem mentioned. And we gotta put the axis here, X and Y axis. Now we go ahead and solve the problem. Okay? Draw the object, draw the surface. 3, identify the forces. 4, draw the X and Y axis. Identify the forces. Here you go. Try to deduce the direction of the acceleration from the net force in item 3, right? Draw the X and Y axis. So there's one more thing here missing. Here you go, one more. If you look at this problem here, since we do not have any force in the vertical direction here, the only force in the vertical direction are the weight and the normal, it's fair to conclude that the net force along the y-axis is going to be 0, okay? And the only force that's left is going to be this force parallel to the surface. If this, because the only force being left is going to be this force parallel to the surface, we can guess that the acceleration is going to be also parallel to this horizontal force. Okay, and here you go. I'm even putting it with the same color because they're in the same direction, okay? They're not the same thing, but they're in the same direction. And now we can go ahead and proceed with the solution of our problem. We identify the forces. There are 3. There are only 3. The weight, the normal, and F. Let's get here. Here you go. I want this one here. Net force is equal to my N ends up being 3. Okay. I'm going to here write that as F1 plus F2 plus F3. And I do not need the summation anymore. F1, F2, F3. And I identified all those forces, what they are. One is the weight. The other one is the normal. And the other one is the force F. Okay? And then we break it down into X and Y components. Okay? And let's get the, no, this is not what I want. Okay, that's the one I want. Here you go. That's what I want. This is a two-dimensional problem. Consequently, you do not have this component here of the force, right? Let's see if I can. No. Do it in a nice way. I gotta go. This one. Okay. All I have to do here is to change the subscript now. Are you following? All problems, gotta be solved in this way. Okay. First, I'm going to put as a vector, okay? And then I'll take out the vector because it's going to make it easier for our. And here too is going to be a vector. Here's going to be a vector. Okay. There's a reason why I'm doing that. The force along the x direction is just the force F. Let's see here. Force of 1 Newton. Okay. So I'm just gonna put it F here. The force along the y direction is going to be the weight and the normal. Okay. Analyzing the problem, we can see that since we have just one force, this here can be written down as a single scalar. And the vector acceleration doesn't need to be written down as a vector anymore, it can be written down as a scalar. We take a look at the drawings here for the normal and the weight. There is no component, there's no other component along the y direction. Consequently, those two forces along the vertical direction, they must cancel out. Okay, so you can write like that, magnitude along the minus y hat direction. And we do the same for the n. Magnitude of n along the plus y hat direction. Since there is no acceleration along the vertical direction, you know the acceleration is going to be 0 here. So this problem that you see is in reality two problems. One along the horizontal direction, that's given by Newton's second law of motion, and the other along the vertical direction, that's solved by using Newton's first law of motion. Okay? And now we have the system of equations right here. I'm going to erase this guy here that's bothering me. Here you go. Okay. Here is going to be 1 Newton. I told you that the mass is 1 kilogram, right? Here we can write that y hat equal to 0. But let's concentrate about find the mass. That he's asking just the acceleration of the mass. So you don't have to worry about this second equation here, because the acceleration of the mass is determined from this equation, right? But let's keep on using that. The acceleration is going to be 1 Newton divided by 1 kilogram, okay? Which, by the way, is going to be 1 kilogram meter per second square, right? Divided by, let's see how I'm going to do it. I'm going to do like that. Divided by 1 kilogram. Kilogram cancels out with kilogram, and then what we have? We have 1 meter per second square. Okay. So we solved our problem. We don't need to worry about that, because I can ask, for instance, what is the, I can ask in the next level of this problem, what is the value of the normal, right? I can ask you that. Then you go ahead and use the second equation that's left out, right? This one here. We can put this in evidence. Okay, we can, y hat is getting into evidence. And solve for the normal. But before solving for the normal, we have, right here, no. we gotta put the mg here, right? Or even better, let's do it this way first. You know, y hat cannot be 0, so the only way for this equation to be satisfied is for this terms in the parentheses to be equal to 0. Okay, so here go the normal end up being equal to W, which by the way is magnitude of W, just because this negative sign cancels out, right? Which by the way is mg. Okay, in this specific case, the normal ends up being equal to the weight. (938). Let's talk about the force of friction now. I have to elaborate. Let us now elaborate on the force of friction. At this point in time, you already know that there are two forces of friction. There are two forces of friction. The force of static friction and the force of kinetic friction. Okay, kinetic or slash diameter, dynamic friction. Either kinetic friction or dynamic friction. Either way, it's fine. Let's take a look here at my drawings. Let's see if I have a drawing that explains this force of friction. Let's take a look at the other one. Any questions so far? Yeah, let's see. Let's try this one here. Trying to find the slide that has a nice illustration of the force of friction. If I can't find it here, I will have to draw it from scratch, okay? Okay, I got it. Okay, so here you go. Let's start with the force of static friction. 209. Okay, 209. I need you to understand how this force of friction behaves, okay? So here we go. Here we go. Behavior of the force of friction. We're going to start with the force of static friction. Force of static friction. Okay, like that. But just okay. So best way for you to understand this force of static friction is by looking at this figure, okay? Is by also playing what I call playing the movie. And I'm gonna get something else here. Yeah, here you go. That's what I want. X and Y, okay? Okay, so if an object is sitting here at rest and there is no force being applied to this object, that's why I put it F equal to 0, right? A very small arrow here denoting that the force is 0. It means that the static friction, the force of static friction must be 0 as well, okay? Make sense? Velocity is equal to 0. Net force must be equal to 0. If this force is 0, this one, the force of static friction must be 0 too. We're using here the method of induction, right? Here you go. And now I decide to apply a force of 1 Newton. And the object is still at rest. If the object is still at rest, it means that the force that preventing it from moving is still the force of static friction, which has the same magnitude of the applied force there. Okay? And then we decide to increase the force to 2 newtons. And the object is still not moving. What does it mean? It means that we must have a force of static friction. There's also 2 newtons. And by the way, this happens in real life, okay? This happens in real life. It's not just here in my drawings, but in real life. Let's see. Molly is asking, is the acceleration always go the same direction as the net force? Yes. Don't forget, the acceleration always goes in the same direction as the net force, right? Not a single force, but the summation of all the forces. Always. That's what this law means, right? And let me make this drawing nicer. Go. X and Y. X and Y, okay? And then it comes to a point where the object is on the verge of motion. It's on the verge of motion. You see, it's all those lines here that you can see, is illustrating the fact that the object is about to move. Okay? Make a little bit thicker, and I want it to be black as well. Yeah. So there is a point that the object comes to be on the verge of motion. That's how it works, okay? A force just above 3 newtons, in this case, for instance, if you apply a force just above 3 newtons, the object starts moving, okay? Verge, let's put it here, verge of motion. At this point, whenever the object is at the verge of motion, the force of static friction gets a maximum value, reaches a maximum value, which I call force of static friction, maximum value of force of static friction. And by the way, every force of static friction is dependent on the normal. Okay? Every force of static friction is always proportional to the normal, whether dynamic or static. And this maximum value of the force of static friction is going to be equal to the normal times this coefficient that I call the coefficient of static friction, which I'm giving here a value of 3 newtons. Okay? If we are to plot if you're going to plot, okay, the force of static friction against the applied force, we're going to get something like the following. Here you go. I'm going to erase this one here. We're going to get something like that. Okay? Let me erase that part too. At least you know. Okay? Applied force, force of static friction. So as the applied force increases and the object is still at rest, it means that the force of static friction is also increasing. Okay? Until it reaches a maximum value. This maximum value is given by the maximum value of the force of static friction, which is given by that relationship that you saw there. Okay. Oh, and by the way, very important, it is the force, the maximum value of the force of static friction that's equal to that relation that you saw. Okay. Between this value and this value, the force of static friction depends only on the net applied force. Let's put here, let's put here net force. Let's leave applied. Okay, let's leave applied. So can you remember that? Okay. Then, we're going to talk about something else, right? We're going to talk about once we exceed this maximum value of force of applied force. Okay, there you go. The object start to move. Behind this. Okay. Oh, it's Newton. Yep. Yeah, here you go. 3.1 Newton. Okay. Once we reach this just above the maximum value of the force of static friction, when the object was on the verge of motion, now object on the verge of motion starts to move. Okay? Starts to move. Not only starts to move, but it also starts to accelerate if you don't do anything. Okay? And the force that was the force of static friction now becomes the force of kinetic friction. Okay? And now I can show you the other graph. Here you go. The other part of the graph, here you go. Initially, we are applying a force. The object doesn't move at all. As I increase my applied force, the force of static friction counters the applied force until the applied force reaches a value that is equal to the maximum value of the force of static friction. I increase the applied force just a little bit, and the object starts moving. And when the object starts moving, now you no longer have the force of static friction, you have the force of kinetic friction. okay? And the object starts moving. It happens that the force of kinetic friction is usually less or equal than the force, the maximum value of the force of static friction, okay? That's the story. That's why I put here acceleration greater than 0. If this applied force is greater than the maximum value of the force of static friction, it means the object is going to accelerate from this point on. And I'm going to increase the thickness of this line, right? So right in here, right there, okay? And as I increase the applied force, the object moves with an acceleration. 952. Any questions about that? We're going to solve some problems, okay? So what you have to know, let's see if I can, there are two forces of friction, the force of static friction and the force of kinetic dynamic friction, okay? So the force of the let's document everything that I said, right? The force of static friction applies whenever the object is at rest, whereas the force of kinetic friction applies whenever the object is moving, either with constant velocity, moving, okay? That tells everything. If the object is moving with constant velocity, you have the force of kinetic friction. If the object is moving with acceleration, you still have the force of kinetic friction, okay? So assume that an object is initially at rest. Then we apply a small force. Is initially at rest over a horizontal surface. Okay? If we apply a small force in the horizontal direction and the object does not move, it means that there is a force of static friction countering the applied force. Okay? I'm just repeating what I mentioned before, right? If we increase this applied force and the object is still at rest, it means that the force of static friction increased accordingly, and it is still countering the applied force. Okay? There is a point in which the applied force, there's a point in which the applied force reaches a value that is equal to the maximum value of the force of static friction At this point, the object is still at rest, but it is on the verge of motion. At which verge of motion. If we increase the applied force just above this value, and here you go, you want to put it here, Fs max, right? 1, 2, 3, 4, low. If we increase the applied force just above this value, comma, the object breaks out from rest and it starts moving. Break out from rest, comma, it starts moving, and the force of static friction becomes the force of kinetic friction, which, by the way, most of the time is less than the force of maximum value of the force of static friction. Okay, so here you go. Oh, I have to write down here something too, right? So an object is there's a point. At this point, the object is still at rest, but it is on the verge of motion. Okay. And by the way, let me put a very important equation here. Here you go. The maximum value of the force of static friction is given by that equation. And this coefficient that you see right here is documented in tables, okay? Where, here you go, where mu sub s is called the coefficient of static friction, which is documented in many tables. Also, we have the we have the following inequation. Okay, which can be here written down like that. Now, if we increase the applied force just above the maximum value, right? Just above the maximum value of the force of the static friction, the object breaks free from rest. Let's put it this way. Breaks free from rest. You start moving, and the force of static friction becomes the force of kinetic friction. And by the way, the force of kinetic friction has an equation that's similar to that one of the maximum value of the force of static friction. Okay. Where mu sub k is called the coefficient of kinetic friction, which is also documented in many tables. In general, mu sub k, mu sub k is less or equal in general. Mu sub s. Okay, and what else? Also. Consequently, right? F sub k is less than or equal than f sub x max. So sub f max. Like that. Okay. So it's 10:02 already. Any questions? So let's take a look at the attendance here today. Today is the 14th. Audrey Aguilar, are you there? Yes, thank you, Audrey. Matthew Aguirre. Let's see if Matthew is here. I don't see Matthew. Next is Brianna Carrillo. I don't see Brianna. Okay, let's see. Jazzy Castellano. Are you there, Jazzy? Okay, I'm gonna put a star here to Jazzy. Gabriel Contreras.
Here.
Thank you, Gabriel. Liliana Cortez.
Here.
Thank you. Next, Juan Escalera. My goodness, Juan is not coming in. Next, Molly Fitzgerald.
Here.
Thank you. Henry Kim.
I'm here.
Okay. Next, Ruth Mandujano. Thank you, Ruth. Noemi Martinez. Are you there, Noemi? Okay, I'll put a star here. Danae Miller.
I'm here.
Thank you, Danae. Ramon Olivares.
Here.
Thank you. Taylor Thorne. Let's see, Taylor. Noemi, okay, thank you, Noemi. This one look like Taylor is here today. Stephanie Ramos. Doesn't look like she's here either. Jeremiah Reyes. Thank you. Next, Sean Rosario. Hello, Sean. Okay, I'm gonna put a star here. And next is Ali Standard. Thank you. Jason Strait.
Here.
Thank you. Next is Elena Trujillo. Standard. Are you there, Elena? Okay, put a star here, her name. Jason Valadares.
Here.
Thank you. Next is Stephen Vadhapali. Doesn't look like Stephen is here. Next is Larell Williams. Thank you. Let's see. Nuhamin Wandimu. I don't see Nuhamin here. Alia Zavala. Okay, 15, 16, 17, 18. Yeah, okay, so let's give another chance here. Jazzy, are you there? Okay, Sean? Are you there, Sean? And Elena? Oh, Sean is here? Was that Sean that
No, but Jazzy said here in the chat.
okay, Jazzy said yeah. Okay, thank you. Okay. And then Elena. Okay, so let's go for our break now. 10:07. Break 10:07 until 10:07 a.m. until 10:22, right? Sean is here too. Okay. Sean. Okay. Okay, so I see you in 15 minutes. Okay, I'm back here. Let's get an example. Let me give you an idea of the values of the coefficient of static friction and kinetic friction. So you can have let's say, the second law of motion. The law of motion, we have to talk about the law of motion, types of forces, gravitational force. Let's see, normal force. Okay, good. We must have a little table here. Those coefficients of static and kinetic friction, they are obtained experimentally, and here's a table. Okay, it depends on the type of material. If it's glass on glass, now suppose that we have a tire that's made of glass. I don't even need to have a tire, just a block of glass in contact with a glass surface that's dry. Look at the coefficient of static friction is 0.94, whereas the coefficient of kinetic friction is 0.4. In general, this coefficient of kinetic friction is going to be less or equal than the coefficient of static friction. And don't forget that equation, the coefficient mu sub s times the normal applies only to the maximum value of the force of static friction, right? Here you go, ice on ice, okay? 0.1 for static friction, a cube of ice over an icy surface, right? That's the coefficient of static friction, 0.1. And the coefficient of kinetic friction is much less. It's 20% only. Rubber on dry concrete. Okay, so your car, whenever you're driving your car over a concrete surface that's dry, concrete freeway that's dry, right? That's the coefficient of static friction that we have, 1.0. And that's coefficient of kinetic friction that you have. The coefficient of static friction applies whenever the tire of your car is just rolling without slipping, okay? And here, this coefficient of kinetic friction applies whenever you lock the wheels on the pavement. Okay. Rubber on wet concrete, so the coefficient of static friction and kinetic friction, they decrease compared to dry, right? And there is also a coefficient of kinetic and static friction not for dry concrete, but for the pavement, the asphalt, okay, which is slightly less than that of concrete. They don't have here for the rubber on asphalt, on dry asphalt and wet asphalt. They don't have here in this table. Steel on ice, 0.1, 0.05. Steel on steel, 0.78, 0.42. Teflon, okay? Look at the coefficient of static and kinetic friction of Teflon. They are the same, right? But it's very low too, it's 0.04. Teflon is that material that's in the bottom of your frying pan that doesn't let your eggs get sticky there. Okay, and wood on wood, 0.35, 0.3. Okay, keep that in mind. Those are real life values of these two types of coefficient. Okay, and let's do this example here in the book. Some of you have been asking me to solve some of the examples in the book, right? Okay, let's do that. I'll put it side by side. Oh, I also have, see, also have a table of coefficient of, okay, that's 2023. That's not 2024. Let's see here. I'm gonna copy and here you go. Table of coefficient of static and kinetic friction. Rubber on concrete, okay, steel on steel, so on. Synovial joint in humans. Look here. Those synovial is in the knee of humans, right? Look at the coefficient of static friction. It's amazing, right? It's very low compared, even compared to Teflon. It's much lower than that of Teflon on Teflon. 75% lower. Now let's example. Example 9 in the book, chapter 4, right? Yeah, chapter 4. Here you go. Example 9. Okay, so we have the situation in which a skier is standing motionless on a horizontal patch of snow. It's at rest. Okay, the skier is holding onto a horizontal tow rope, which is about to pull her forward. The skier mass is 59 kilograms, and the coefficient of static friction between the skis and the snow is 0.14. What's the magnitude of the maximum force that the tow rope can apply to the skier without causing her to move, okay? So we are going to come up with the first step is to come up with a free body diagram. And you don't have to draw the skier, or you can draw the skier as though it is just a a block, right? Here you go. And here you go. Here's my skier. Here you go, standing right in here. My skier, the velocity of the skier is 0, is at rest. Example, I'm gonna put here example 9, chapter 4 book. Chapter 4 book. You go. So, and this here is being subjected to a force. Okay, and I'm gonna be here, put it right down F, right? So what's given? Going back here. Mass of the skier. What's the mass? 59 kilograms. The coefficient of static friction between her and between the skis, right? And the surface is 0.14. Here you go. Here you go, mu sub s. 1, 2, 3. I like lowercase m. What else do you have here? Okay, find what's the magnitude of the maximum force that the tow rope can apply to the skier without causing her to move. Okay, so basically is what he's asking us to do is to find the static maximum value of the force of static friction. That's what she's asking us to do. Okay, that's what. And let's go back to the drawing board here. Here you go. I'm gonna put a different color here, red, and then I'm going to put it right in here in blue color, this nice blue, and invert the direction. Yeah. On the top of that, I will label it FS max. Okay, and I'm gonna put it in blue color. Okay, that's what the problem he wants you to solve. Okay, he's asking you this F here, and you find this F by finding this force here. Okay, so instead of putting F max, find the maximum force that the tow rope can apply on the skier without causing her to move. Okay? Which basically finding out what is the force of maximum value of the force of static friction. Okay? That's what it's all about. So let's solution. The maximum value of the force of static friction is mu sub s times n. We have mu sub s, right? But we still do not have n. Okay? We do have mu sub s, but we do not have n. But n can be found easily from by identifying the forces that act in the skier. Not only we have this force F, not only we have this force of static friction, but we also have the weight and the normal. Here you go, here's the weight. I'm gonna put a different color. Green, yeah, let's use green here. Oh. Oh. Yes, mama. Yeah. Okay, weight. I'm not gonna put that in green color. And we also have a normal. Okay, I'm gonna put it in a different color as well. Let's see, what about this color? Good. Now let's put this one here. It's better. And normal. The skier is not accelerated along the vertical direction. Consequently, the normal must be equal to her weight. Okay? You go from the free body diagram. From the free body diagram, the normal is equal to the weight mg. Okay, so we go ahead and place it right in here, mg. And now it's just a matter of plugging in the numbers, and finding out what this maximum value of the force, right? So it should be 0.14. 0.14 times 59 times 9.8. I'm getting 81 newtons. Is that what he has here? So yeah, 81 newtons. Okay. Let's see another one. Okay, now is an example of kinetic frictional force. Okay, so I sled example 10 now. In the book chapter 4. So let's see. I sled the speed of 4 meters per second is a speed. 4 meters per second. Horizontal surface, there's no exert a kinetic frictional force on the runners of the sled. So the sled slowed down and eventually comes to a stop. The coefficient of kinetic friction, okay. Now coefficient of kinetic friction here is 0.05. What's the displacement x of the sled? Okay. The sled and its rider are moving at the speed. Those are the, what is displacement? What's the displacement? What is the displacement of the sled? Okay. Okay, remember is we are dealing with force of kinetic friction, right? Let's go ahead and just like before, let's come up with our free body diagram. Okay, it's going to be not going to be slightly different because the guy is laying down, right? Let's put like that. Okay, so initially it's moving with this initial velocity, 4 meters per second. We do know that there is a normal, like before, there is a weight as well. That doesn't change, right? There's a normal force, a weight, and there is this force of kinetic friction now that's applying a force in the opposite direction to the slider. Okay? So little by little, this guy is gonna lose speed, okay? So because we do have a force of kinetic friction, we must also have an acceleration in the opposite direction. I'm making, just like before, I'm making the acceleration the same color as the force vector. I'm gonna put here at the top of the velocity, okay? Just to illustrate the fact that this velocity must decrease as time goes by, right? Because the acceleration is contrary to the direction of motion. Eventually, this slider is gonna come to a stop. Here you go. It's gonna come to a stop. Final velocity, 0. Okay, and when the velocity goes to 0, there is no more a force of kinetic friction. And, okay, I'm going to do something like that. Here you go. He's asking, what is this displacement here? And we can even put another frame here in our movie, right? let's see. This one is the initial position. Yeah, I'm going to bring to front. Yeah, okay, here you go. But here is no longer 4 meters per second. Let's say anywhere in between, let's say 2 meters per second, right? And the arrow must have shrunk by half. The acceleration doesn't change because the force of kinetic friction doesn't change. It's not turning out to be good. Let's see. I'm gonna move a little bit more to the left so I have enough space. Okay, here you go. Yeah, here you go. Now I have more space here. Like that, right? Next. Oop. And then I must have those two in the next slide, like that. I'm gonna make this one completely transparent. Okay. Or even better, I'm gonna move this a little bit to the right, further right, yeah. Okay, and now we no longer have an acceleration because the object came to a stop, right? So here you go. Initially, the object is here, moving at 4 meters per second, and we have this force of kinetic friction. A little bit later, the object is slowed down to 2 meters per second. The acceleration is the same because the force of kinetic friction didn't change until the object comes to a full stop. Okay? Along the way, I have this motion diagram that you can see. Yeah, okay, good. And then we have this displacement that is asking us to find this distance here from here until here. Okay, and okay, right in here. Even better, yeah. Let me go a little bit lower than that. The displacement here is going to be delta x. Delta x, like that. That's what they are asking. I have to put, there's one more thing here missing, right? I gotta put, oh, okay, there's no force here anymore. So what we have to do here, we have to find the acceleration first. From the acceleration, we find what the displacement by using the kinematics equations, the equation of kinematics, okay? So here you go. First step. We must first find the acceleration. Or let's see, not acceleration, but the deceleration, right? Deceleration of the object. We do know that, and how do we find the deceleration? We find the deceleration by using Newton's second law. Net force along the x direction is equal to mass times acceleration in the x direction. And let's not forget that the only force that we're dealing with in the x direction is going to be the force of kinetic friction. There is no acceleration along the vertical direction. Consequently, the normal is going to be equal to the weight. Like that. Okay? Here should be K. Here should be K. Don't forget that force of kinetic friction, right? Mu sub K times N. But because the only force acting in the horizontal direction is the force of kinetic friction, this here, oh, already put that there. Okay. Where 1, 2, 3, where? I'm gonna put it here, like that. Strictly speaking, I should be putting a negative sign here. Okay? Because the axis, positive axis is to the right, strictly speaking. Okay? And if you have a negative sign here, you must have a negative sign here as well, okay? And then we're gonna get a negative acceleration. Okay, and now we solve that for the acceleration. Solving for the acceleration. We have something like that. Look what happens. In this specific case, the mass on the left side cancel the mass on the right side. Okay? Which simplify our problem. I'm gonna cancel the mass here and the mass here. Okay? And we have the values, 0.05. We have G, we can find out the final answer, right? For the acceleration. Get your calculator or get your spreadsheet, 0.05 times 9.8, 0.49. Equal minus 0.49. That is meters per second square. That's the acceleration. That's part of the problem. First step of the problem. Now we have to find out what's the distance that the slider travels, right? We need that to find this distance. And which equation are we going to use? Okay, it's going to be the equation for uniformly accelerated motion. And we have that equation v squared, final velocity, right? Square is equal to the initial velocity square plus 2a delta x. Remember this equation? We want to find this guy here. Okay, we want to find this guy right in here. The initial velocity, we already know. It's 4 meters per second. Here you go. I'm gonna put it initial here. Okay, and we can also, because it came to a stop, the final velocity is gonna be 0. V is equal to 0, final velocity. Finding delta x is minus equal, right? This guy here is 0. This guy is 4 meters per second square raised to the square, 1058. The acceleration, I found out that is a negative value, 0.49 minus 0.49 meters per second square. In the next step, this, let's see, then I'll get rid of the 0, right? This negative goes outside. Negative cancels out with negative. Okay. 4 raised to the square is 16 meters square per second square. Okay, this 0.49 becomes what? Multiplied by 2 becomes 0.98. 0.98. 0.98 meters per second square. We solve for delta x. Delta x is going to be equal to, oh, what's happened here? Okay, okay, like that. This value here, 0.98 meters goes downstairs. Second square goes upstairs. Like that. And then we can continue solving this problem. Second square cancels out with second square. Meter cancels out with meter square. And then you gotta do the ratio here. This ratio is approximately 16, a little bit more than 16. Okay, I don't want to bother with doing this calculation. Let's see. Yeah, it's approximately 16 meters. A little bit more than 16 meters because we're divided by 0.98. Let's see if it's what the book found. The procedure here, it's the same as I did. Let's see. Solution. Yeah, 16. Okay. 16 meters. 11 o'clock now. Any questions? Am I missing anything here? So make sure you practice more of those problems, okay? Let's take a look at the book. Look, let's take a look at the chapters here that I laid down before. Here you go. What we have covered so far, right? We covered this one. We covered this one. We covered this one. Okay, vector coordinator Newton's first and second laws of motion. Yeah, we covered that one too. So much that we're doing our equations all in vectorial equations. We didn't cover this one yet. Types of force. We didn't quite cover this. But let's take a look here. Let's take a look at the book. Let's see if we cover these types of force. Newton's third law, types of force. Yeah, okay. Yeah, this one is very qualitative. I can talk about the gravitational force, and then there are two other important forces that we're not gonna see here in this course: the strong nuclear force and the electroweak force. Okay, just memorize those three: gravitational force, there's the strong nuclear force, there's the electroweak force, and what he didn't mention, there's the electric and magnetic force. Okay. And gravitational force, we didn't cover that yet. We cover only the gravitational force nearby the surface. But what he's talking about here, the gravitational force that he's talking about, is the gravitational force whenever objects are far apart from each other. Okay, we're going to cover that. We didn't cover that yet. Normal force we covered. Static and kinetic frictional force we covered. Tension force we did cover. No, equilibrium application of Newton's law of motion. Yeah, we did that. And which means that examples of first law. And here should be examples of second law. We already covered some examples. So we are left only with those two sections here of the book, okay? 11:04. Let's take our break now. Any questions before we go for the break? Okay, 11:05 a.m. till 05, not 06. Till 11:20 a.m. Okay. If you don't have any questions, let me just give an opportunity for someone. Here you go. Elena, are you there, Elena? Okay, Elena is not answering. Okay, so let's go for our break now, and I'll see you in 15 minutes. I'm back here, and let's see if we can finish chapter 4. Newton's third law of motion. So we have two laws of motion so far. Okay. Newton's first law. I'm going to put it between quotes because it's not exactly a law of motion. Gotta memorize that. Newton's second law of motion. F equal to ma. And then we have finally, we have Newton's third law of motion. This one doesn't have a quote. This one doesn't have. I like that. First law of motion, second law of motion, third law of motion. Let's talk about the third law of motion. You have to remember. Okay, so if two objects interact between each other, It's just a statement, okay? There is nothing much of a formula here. An interact means if two objects exert a force, okay, between each other. If two objects, 1 and 2, object 1 and 2 interact with each other, right? Exert a force, interact between, here you go, let's put it this way, between each other, interact with, no? Exert a force between each other. Then the force that one object 1 applies in object 2 is equal in magnitude and opposite in direction. So I'm going to formulate that, okay? That's how you, one form of this statement. Let's put in another form. Let's rephrase that, okay? Let two objects, 1 and 2. If let two interacting, object 1 and 2 interacting with each other, okay? That's another way of stating this third law, okay? Let two objects, 1 and 2, interacting with each other. If the force that object 1 applies to object 2 is, I'm going to use my notation here, okay? Let's see here. Here you go. I'm gonna use this notation here. If the force object 1 applies to object 2 is, is F of 1, 2, okay? Force that object 1 applies to object 2 is written as F12, and the force that object 2 applies to object 1 is F1, okay? Do you notice that I put a vector here? I put a vector here, all right? Then there is a relationship between those two forces. That's what Newton's third law is all about, between these two forces. And this relationship is given by the following formula. F of 1, 2 is equal to minus F of 2, 1. Equal in magnitude, but opposite in direction. Okay? Let's see how the book formulates this third law. Okay, let's see. Newton's third law of motion. Okay. Okay, whenever one object exerts a force on the second object exerts an oppositely directed force of equal magnitude on the first object, okay? That's another way of formulating Newton's third law of motion. Now you choose the best way, the best one to memorize, okay? Definition in the book. The definition is written down differently, but they mean exactly the same, okay? copy that definition from the book. Formulation from the book. Huh, it's not copying it. Strange. Yeah. For some reason, it's not copying it. I don't know why. Copy. See, copy when I try to paste there. Doesn't paste it. Okay. I'm not going to copy, paste it here. Okay. Examples. Examples. So I'm gonna give you some examples. Right here. Let's see. Here you go. Consider this case here of a mass, okay, above the surface of the Earth. And this mass may be in free fall, okay? This mass can be in free fall. Earth is object number 1. The object here, the mass here is object number 2. This object on number 2 has a weight. Okay, it has a weight. And this weight, what is this weight is all about? This weight is the force that the Earth is exerting on object number 2. See that? mg. mg is the force that Earth exerts on the smaller mass m, force that 1 exerted in 2. Okay, if the Earth is applying a force to this object, it means that this object is also applying a force on Earth. At the center of the Earth, you have this force of 2 applied in 1. So if this object is 1 kilogram, its weight is going to be approximately 10 newtons. Okay? The Earth is applying 10 newtons of force in this object. Consequently, this object is also applying a 10 Newton force on the Earth, but it's going to be the direction of the force is going to be opposite. That's an example. Okay. We can do free body diagrams. And that's what we have right in here. We have a free body diagram in which I'm considering only the smaller mass, number 2. Okay. And we are ignoring the Earth. That's why I put it a dashed force here. If we have 2 magnets, we have something similar. If place the north side of one magnet facing the north side of the other magnet, you're going to find out that those forces are repulsive. Have you ever done this experiment, right? And then I'm going to, here you go. Minus, and I'm gonna put equal, okay? Equal, and then symbol right in here. Yep. And I should do the same for the previous ones. Here you go. You do the same here. Third law. Oh, the other way also works. If the south pole of one magnet is facing the north pole of the other magnet, we have exactly the same situation. Force that one applying the other is equal to minus the force that the other applying in 1. Okay? But there are more. Here you go. If I apply a force on the wall with my hand, okay, so here you go. Here's my hand, here's my arm, here's my hand. That's the force. My hand is object number 1. The wall is object number 2. Here you go. F1 applied to 2. It means that the wall is applying a force equal. in magnitude and opposite in direction. Another one, here you go. A string attached to an object, right? So here you go. I'm gonna play the movie here for you. Play the movie here for you. Here you go. String. String is object number 1. The mass here is object number 2. Okay. And then I decide to pull object number 1 with the string. Here you go. Force of 1 applied to 2. Here you go. It's better if put like that, right? What does it mean? I did the, okay. All I have to do, okay, so now I'm gonna copy and paste. Okay, otherwise I'm gonna lose important things here. Okay, here you go. That's how I illustrate the force that a string is applying to the block. Okay. The string is interacting with the block. Consequently, I missed it here. Consequently, the block is interacting with the string. And what I have to do, all I have to do is to invert the direction of the force. Okay. I'm going to display so even better. You know what? I'm going to change the color. So it's, here you go. Force that 2 exerts on 1. Like that. Okay. Don't need that anymore. So if you have the Earth and the Moon, here you go. Earth is object number 1, Moon is object number 2. Okay. Force that 2 exerts on 1, the force is minus the force that 1 exerts on 2. And we can also come up with, going to come up with another illustration, okay? So here you go. An object resting over, I'll call this one object number 1. And I call, let's say, a table. Suppose that we have this object lying over the surface of a table. Right? Surface of a table. You already know that this object here is feeling a force that's normal, right? Here you go. I'll put like that. And I'll put it 1 to the side. Objects 1 and 2. Mass and table, right? You already know that the table is exerting a normal force on object number 1 that I'm going to call N of 2 applied to 1. Subscript, like that. If the surface here is exerting a normal force on this object number 1, it means what? It means that the object is also exerting a normal force on the table in the other direction. And let's see, begin arrow. Like that. Okay, that's 2 in 1. One in 2. Like that. Let's put that in different color. And so on. There are many other examples in which something like that happens. Okay? Many other examples in which something like that happens. And the best example is this one here of the 2 blocks. 2 blocks touching each other. Friction is negligible. I love this problem here. And we have this force here applied on the side of mass number 1. Okay, let's do that as an example. Let 2 masses on horizontals, let 2 masses M1 and M2, M1 and M2 lying, sitting on a horizontal surface. Horizontal frictionless surface. On the horizontal, frictionless surface. A force, let's make sure, let 2 known masses, M1, M2, a known force, F, is applied along the horizontal direction on mass, what, 2 or 1? Let's take a look here. On mass 1. On mass 1. Find the acceleration of the whole set of masses. Would be the first one. Okay. Find the acceleration of the whole set of masses using both masses. Find the acceleration of the whole set using both masses as the system. Then good. Okay, then we are going to repeat this problem, but you're going to repeat it in a different way. Find the acceleration of mass 1 alone using it as the system. Okay, and finally, let's see. Let's put it this way. Find the acceleration of the masses, of the 2 masses, using 3 different free body diagrams. diagrams. Okay. Okay. Here you go. Using both mass as the system, I'm gonna using mass 1 alone as the system, using mass 1 alone as the system, using mass 2 alone as the system. Okay. That's it. Solution. Okay. The easiest one is this one right in here. Okay, that's the easiest one. The other two are not that very intuitive, and I'm going to, and I hope you understand, because I'm going to do it in 3 different ways. Okay. Okay, here you go. Friction is negligible, right? We have this force F being applied to mass number 1, which is touching mass number 2. When I mean that the two masses are a single system, what do I mean about that? I mean that I'm going to look at these two masses as though they are a single object. Okay. I'll be treating those two masses as though they're like I said, as though they're a single object. Just like I have it here, okay? M1 plus M2. And so the normal will be given by the normal of 1 plus the normal of 2. The weight, the net weight is going to be the weight of 1 plus the weight of 2. In this type of solution, we do not need to use Newton's third law of motion, but I'm going to solve it anyway. Because the surface is frictionless, we have just this single force here in the horizontal direction. The acceleration must be in the horizontal direction as well and pointing the same direction as the force. Okay? So how do we solve it? Solution I. Nope. We go. I go. So the situation is like that. F net equal to net mass times acceleration, right? Net mass should be M1 plus M2. This equation can be broken down into 2 different equations. One along the horizontal direction, the other along the vertical direction. And net force along the horizontal direction. I don't need to put the vector symbol anymore. M1 plus M2 A sub X. Oh, like that. I want to find this acceleration here. Oh, no acceleration, right? Like that. But we still have another equation here along the y direction. It happens that the mass doesn't move along the y direction. For this reason, that must be equal to 0 in this set of equations. I want to find acceleration. Okay. And I don't need that. I don't need that at all. Okay. So here you go. But I'm going to, this net force along the x direction is going to be that force F. Okay. I'm going to put it here. Like that. This net force along the y direction is going to be the normal minus the weight. Okay. Normal of 1 plus normal of 2, right? Like I drew there. Oh. Something wrong here. Yeah. It's not typing here. Why is that? Let's see. Okay. N1 plus N2, right? Minus W1 minus W2 equal to 0. But we all we have to do is to worry about this guy here. Okay, so I'm going to neglect that for now. And if you need to go back to this one, we go back to this one. Okay, we want to find out the acceleration, and all you have to do is solve for a sub x. I already know that the acceleration along the y direction is 0, right? F m1 plus m2, like that. Like that. That's the first solution. Straightforward. Okay. What about the second, a second different way of solving this problem, right? Using mask one alone as the system. Well, so the is illustrated right in here. I'm doing here. Let's see here. Yeah, I want to do this one first. Okay. Okay, so here you go. I'm going to draw a box around the first mass only. I'm doing that to tell you that I am neglecting. I'm zooming on the first mass only. It's not that I'm neglecting the second mass. No. It's not that. Okay? I am zooming on the first mass only. And let's put it, yeah, here you go. Free body diagram. And we have to identify the forces. Let me remove those forces here for now. Okay, here you go. M1. Yeah, we don't need that. Here you go. M1. This one here is M2. 1150, we are almost there. So here you go. I'm gonna put my box around this mass, and I'm going to look at all the forces that are mass number 1 is subjected to. Okay? Here you go. One force is this one here that I already told you, right? But then there is another force that this object number 2 applies to object number 1. Like that. And I'm going to shrink it a little bit, because for the object to accelerate to the right, this force here must be less than this other force. And this force here is going to be named as force of 2 applied to 1. Notice that I am using Newton's third law of motion in this specific case, because there is a force of 2 applied to 1, there must be a force of 1 applied to 2, right? Let's do that. I'm going to illustrate this force And I'm gonna make it, let's see how I can make it dash. Nah, I don't like this dash. What about this one? Yeah, better, right? See? Force of 1 applied to 2. Right? That's force of 1 applied to 2. I'm going to, in the next, I'm going to eliminate this one here because we don't have to, because we're looking just at the forces applied to 1. We have 2 more forces, the normal and the weight. But those 2 forces are not going to affect the acceleration. Okay, so here you go. I'm gonna move it to the left, right? Like that. And now, those 2 forces, they don't affect the acceleration. Consequently, we can now start solving the problem. The net force applied using this specific, applied to the mass number 1 using this specific free body diagram is going to be what? F. And now I'm going to, here you go. Now let's do it this way. Here you go. M1 times A, right? Because I have chosen mass number 1 to be my system. Did you notice here? In the previous problem, we used that 2 masses are being our system. Consequently, we have to account for the net mass on the right side. But now that we are considering only the mass number 1 as our system, then I have to have mass 1 only on the right side. And what else I'm going to do? I'm going to write this equation in scalar format, okay? Acceleration is gonna be a scalar acceleration. The net force, is gonna be a net force vector, a net force scalar. And this net force scalar is going to be F, the regular F, minus F of 2 in 1, okay? F of 2 in 1. That's how you solve this problem. Okay, you take into account just the forces applied to the mass number 1 alone. Okay, I didn't finish solving my problem yet. Remember, I want to find out the acceleration here. But in order to find the acceleration, I have to find out what f of 2 in 1 is all about. And I still do not know f of 2 in 1. We find out f of 2 in 1 using the other third free body diagram. Okay. The third free body diagram is obtained by considering just the mass number 2 as our system. And now you go ahead and analyze the forces. You have the force of 1 applied to 2. Okay. In this case, the only force propelling this block to the right is going to be f of 1 in 2. We know that f of 2 in 1 has the same magnitude, but opposite direction. Notice that this force here is not in contact with the second mass, right? But part of this force is being transferred to the second mass due to the contact between M1 and M2. And now, in this specific case, we are going to have that net force should be F1 into equal to M2 times acceleration. And just like before, I'm going to remove the arrow there at the top. Okay. Well, the reality is that the acceleration here we already found. So what we have to do, we don't have to find the acceleration using two different ways. No. What actually we have to do, find the acceleration of the two masses using both masses as the system, okay? Using both masses as the system. Okay. Find one. Let's put this way here. 1, 2. Find the force that 1 applies to 2 using, and 2 applies to 1 and 2. I'm reformulating that, okay? Applies to 1 using mass 2 alone as the system. Okay? And then here you go. What we're going to do here. Verify the acceleration you found in I by using mass 1 alone as your system, okay? As your system. That's how we should formulate this problem. I found in the first item, by using mass 1 alone as your system, okay? And apply Newton's third law along the way. Okay, like that. And now we can invert those equations here. The important thing here is that you learn how to get the equations from the free body diagram. Okay, so here you go. Let's see. Here you go. Notice that we can find out the contact force between the two masses just by substituting this acceleration right in here. Okay. Oh gosh, let's see. This one is M1 plus M2. Plus M2, yeah. M1 plus M2. Okay, I'm going to even put this F outside here and get M2 on the top. And then we repeat for mass number 1. Okay. Now that I found the F of 1 and 2, I can plug this one here and find what A is. Oh, it's already 1202, right? Okay. I'm running, I didn't even notice it. But if you do that, plugging in F, let me finish that so we can all go home. Here you go. Okay, and now we solve put everything here under the same denominator. Let's see. Like that. F, right? You go M1 plus M2. Oh, you can finish that at home, okay? Okay, and then you solve for A here in this one, and then I'm gonna get exactly the same thing. We can stop now, 12:03, and there is office hours right now. If you wanna stay around, let me know, okay? I see you on Wednesday. Let's see here. Pause. Stop sharing more. Not recording anything. Pause. Stop recording. Okay.